So now in this video, we're going to look at the NAND logic gate. It's a lot like the AND logic gate that I showed a while ago now, but it's actually the opposite. So we have two low inputs right here, negative supply, and I can give a high input right there, and it still stays high. Actually, we're getting stray signals there, but it doesn't matter. We have at least one low input, and thus the output is high. And so I'm going to raise this, and there is like a middle ground region, but again, doesn't matter because we have a low input there holding it high. So as long as at least one thing is solidly low, the output's going to be high. So now we have both, or we have this one high, but that one low. And I'm going to set them both high, but first there you can see this is a middle, or not a middle ground region. This is picking up stray signals. So those are bouncing back and forth and rapidly. And so they both looked on. But there we go. We go to the positive supply right there. And now we have a low output there. So we have this. We have this stray signal in the air, which you really can't avoid, I don't think, with these integrated circuits. And I'm not going to touch the metal on there until I touch this. But yeah, there you can see. It can even, my body can, we're still getting the stray signals, but they're different right there. It's being pulled down a little bit more. So, but yeah, I want to make sure I discharge myself before I touch any metal that comes to these integrated circuits because static electricity can fry these really easily. I have a bunch of fried ones, and I definitely don't want to fry this one. But in any case, there we go. We got them both high, the output's low. Now we can like start setting this one low, and you need like one of them solidly low for the, at least one solidly low for the output to be high. And then you can see we got kind of a middle ground region. I see more of a slide right here, and so I think the voltage at the output is not going high and low. I think it's given a middle ground region voltage. So I think that's why both LEDs are lighting like that. And so yeah, now we got a high enough voltage, red LED lights up. That's a high enough voltage, blue LED lights up. And then we're probably getting like 2.5 volts in some middle area right there. That's what I believe. But in any case, we go low and the output is high. That is the main thing right there. So it's the opposite of the AND gate. The AND gate, the output would be low unless all the inputs are high. Then it would be high. So you can see this is the opposite. Now the output's high if any of them are low. The only time the output is low is if all inputs are high. And so AND may seem like it's more useful or something, but actually NAND is far more useful. We can take a couple of NAND gates, I think that's going to be the next video, and make an AND gate. So, you know, if you need an AND gate, you have NAND gates, you can just take a couple and you have an AND gate. Doesn't matter how many AND gates you got, you can't make a NAND gate. So that's why the NAND gate's more useful. It can make any other logic gate plus all kinds of other circuitry, and that, you know, that other logic gates could not make. So you can't make a different gate with just one NAND gate, except for a NOT gate. You know, usually you need more than one, but you can't combine more than one. Whereas most other logic gates, you can't make, you know, just everything else. The NOR gate you can though, but usually people use NAND gates. So we won't dwell on that too much for this particular integrated circuit. We can output up to 25 milliamps of current, sinking or sourcing. And so yeah, we can light LEDs. Just be aware though, there's a 50 milliamp total. So if you're using all four of these, you're going to have to cut that number in half for each one of the outputs. But if you're only using one or two, each those inputs can provide up to 25 milliamps of current, sinking and sourcing. Of course, you have to power the integrated circuit right there, positive supply to pin 14, negative supply to pin 7. And now you'll notice we're using input, input, output, that top left one, number 1, when it comes to the NAND gate. We could use any other one, even though this says 1 of 4. That's really what that means, 1 out of 4 of them. And we have the NAND gate there, NAND gate there, NAND gate there. You can see the inputs I put to a supply voltage. So these logic gates, usually they got like oscillations and stuff going on if you just leave the inputs floating, which can affect the other circuitry. And so you want to make sure you take all the ones you're not using and just lock them in place. You can put either a supply voltage. I have more yellow jumpers than gray jumpers, plus I use the gray jumpers elsewhere. And so as much as possible, I tried to use the yellows to go to the positive supply. But since we have positive up there, and plus I only have so many yellows, I put the grays there to a negative. So that's a little more clear. That's a positive supply voltage, whereas these are two inputs, and that's an output, which you can leave floating. You don't need to attach it to anything. You definitely don't want to short circuit to anything. It's providing power now if you connect it to something. Otherwise, now it's just locked into place. So yeah, that's really about all there is to the NAND gate. So we're going to end it there. Again, this is just a demonstration circuit, not a useful one. I haven't really come up with useful circuits for the logic gates, but I'll try to come up with some. But in case, that's it. Thanks for watching. Make sure you check out one of the other videos I'm posting on the screen, and check out the links down below. They all help out a lot. I'll see you in the next video.